Well, it's a pretty nice day out here, riding around in PEI. You know, it's a bit cold outside, but when you're on a bike, you're always warm. I thought today we'd better talk about moving on from solid mechanics in terms of finite element analysis to looking at fluid mechanics. So before we get started on that, we're going to need to do some math, basically, and talk about how the FEA is different for fluids than it is for solid mechanics. So let's get started.
Yeah, tell them that's going to be hard, the control volumes.
Oh yeah, and just before we get going, I'll warn you, this is going to get pretty fast and you're going to have to try to keep up. So put the pedal to the metal, man. So we're going to talk about first a control volume. You've seen these before in fluids and thermo, and we're going to go to conservation equations. There's the mass conservation equation, which for a fluid is density times velocity, which is a vector, dotted with n, where n is the normal from the surface, and ds is the surface element. So velocity and the normal are dotted, and that tells you if stuff is going across the boundary into the control volume. And if you integrate that, then the result should be the change over time of the mass of the system, of the control volume. And so if you're looking at this, you've got the variable density, you've got the variable velocity vector, and those are the two things. And that gives you an integral equation. Well, that's mass conservation. The next important conservation equation is conservation of momentum. And that's just F equals ma. You've seen that before. Now it's easier to think about if you've got ma is converted into density times volume, which is mass, and velocity, and derivative of velocity. The forces are really surface forces or body forces. And there's only two kinds of forces, and that's them. The surface forces act on the surface, so that's a surface integral. And the body forces act on the body, so it's a volume integral. When you add up those two things, that's F equals ma. Now you can write it in more complicated equations with vector dot products and stuff for velocities, but basically it's the same thing. You've got vector velocity, you've got density integrated over the surface, and that's the momentum part. Momentum added by stuff coming into the volume. Then you've got surface stresses, so you've got stress dotted again with the surface. And then you've got the body forces, which will be, rho g, like gravity. The third would be the conservation of energy equation. And there's nothing special about it. You've seen it before, where the energy of the system, or control volume, is internal energy of the system, U, kinetic energy of the system, and potential energy of the system. The rate of change of that is just simply the rate of change of energy. And the rate of change of kinetic energy is a function of the velocity in and out, and the density. The potential energy is the stress or strain and the density. And the internal energy is the stress or strain and the density. So those conservation equations, mass, momentum, and energy, that's it. That's all we have to work with. So let's look at heat transfer. You've done that already, and that's where the variable you're trying to find is temperature over x, y, z, and t. Mass conservation, not so much. Momentum conservation, not so much. Energy, you bet. But wait, there's more. What about solid mechanics? There, we are looking for stress and strain. Both of them are scalar fields. Maybe they're vector fields, but we can simplify them. Mass conservation, not really needed. It's a solid. Momentum conservation, yep. Energy conservation. But interestingly, those two things collapse in the standard solid mechanics problems. So the sum of forces equals ma is really all we're solving for. And from that, we can get the stress. Now, let's talk about fluids. Well, fluids, we're looking for the velocity, the density, the stress, and they're all vector fields. So we need all three equations, mass, momentum, and energy, in order to make any headway. We've got three vector governing equations, three vector unknowns. So, in summary, heat transfer and structures, they're pretty much covered with one governing equation. They're different governing equations, but it's just one of them. Whereas fluids are three governing equations. For heat transfer, we've got one unknown scalar field temperature. For structures, we've basically got one unknown stress field, and we can relate that to strain just by elasticity. For fluids, we've got density, we've got velocity, we've got stress, but stress we break into pressure and shear stress. So we make it even more complicated by simplifying it. So for heat transfer and for structural, finite element modeling works just great. We do a matrix inversion. If we define boundary conditions and the geometry, we can solve it. For fluids, though, we have to do a matrix inversion for a finite volume method, but we also need an initial guess because we've got so many bloody equations. So it's harder. For instance, for heat transfer, finite element modeling, we've got one differential equation governing, and we can convert it to algebraic equations. And we basically have grid points, say 4 grid points and one vector and one finite element, and every temperature is calculated by its nearest neighbors. So if you extend that to a whole bunch of grid points, every guy is related to the relative neighbors until you get to the edge where you've got the boundary conditions. So if you know the boundary conditions and you know the grid, you can solve the problem. And basically you end up with the result you want is a vector multiplication of a square matrix times the boundary conditions, and that gives you the vector field of the temperature. You've got the same number of equations as the outlet temperatures. So you've got the grid point geometry, boundary conditions, and then you get a solution. Not too bad. We've got to pick it up a notch here. Maybe go into it in a bigger gear. So stress, now we can also get strain by the relations between stress and strain. And for momentum, we can get the stress from the governing equation. But it's the same thing, one governing equation, and each element that we're solving for is related to its nearest neighbors. Almost the same thing, where we've got stress output, a square matrix that's been inverted from the geometry, and the boundary conditions. We can use the elasticity to relate stress and strain, but basically we got this. Now the finite volume method for fluids is quite different, because there, what we're saying is each element is a finite control volume. And so we're going to define the velocity of material in and out of the volume, and the pressures and the shear stresses on the walls. So we've got a whole bunch more things to solve for, and we've got conservation of mass that needs to be solved, and that's a vector equation, kind of like what we've seen already. But we've also got conservation of momentum, which is another matrix multiplication equation. The problem is, we don't know what those matrices are yet. Because of the geometry, because it's not a straight ahead problem, we don't know how to multiply those vectors. So we start off with all of these unknowns, and even if we say density is constant, that's incompressible. Well, that makes it a little bit easier. And if we say it's frictionless, so shear stress is equal to 0, we could also say it's viscous and come up with a relation for shear stress. Or we could say it's turbulent or something else and come up with a turbulent kinetic energy model. Either way, we try to reduce the shear stress with a constitutive relationship. So what do we have left? We've got a simplified flow problem where the flow is incompressible, constant density. We've got a model for shear stress, either turbulence or inviscid or viscous, whatever. But we've got remaining unknowns, which are vector fields, velocity and pressure. And the problem is, we've got two simultaneous governing equations and two unknown fields to solve for. So we can solve it, but not with the same method. So we're getting warmed up here now. So if we've got density times velocity as the outcome, and we've got some square matrix to multiply by the boundary conditions, and for conservation of momentum, we've got velocity and pressure multiplied to get, or from the matrix multiplication from the boundary conditions of velocity and pressure. But we don't know initially what those two square matrices are. So if we start off with an initial guess, we can refine what we think those matrices are from our initial guess and iterate. So that was a quick run through looking at really summarizing the finite element model, which is what's used in solving for structural problems, versus the finite volume method, which is used for fluids problems. Fundamentally, it would be great if you knew the details of the equations and could write them out yourself. But for just getting to use the tools, and as an introduction to these modeling tools, the important thing you know is that for structural mechanics, you don't need an initial guess. You don't iterate the solution. If you know the geometry and you know the material properties, then whether it's solving for temperatures in heat transfer or whether it's solving for stresses and strains, you can do that in one shot with a straightforward, well, not straightforward, very complicated set of linear algebra equations. But if you're trying to solve for flow problems, you can't just start with the geometry and the boundary conditions. You also have to start with an initial guess of the flows, and you need to let it iterate. So it makes it much more complicated to solve for velocities and pressures than it does to solve just for temperature or just for stress or strain. And let's pick this up a bit. Go down, drop down gear, wrist down. And we'll see you again after you've tried some of this analysis.